Hello, so I am back. Results, I hope both of us are back. Yesterday I covered a part of that bending elements from one of the posters on the net with a permission saying yes, you can use all this information. Now I will continue with this from another place, which also in the same this thing. I suggest as we go along you look at the original in case I have skipped something. So you see here it is a manufacturing process by which metal can be deformed by plastically deforming the material and changing its shape. Material is stressed beyond its yield strength. All this I spoke to you yesterday, saying we have a yield stress and then afterwards there will be a permanent set that can occur. So if you take the normal stress strain diagram, you see there is a small kink in it, and then after the plastic deformation is done, eventually before it tears fully below its ultimate tensile strength, you can continue to make operations and you can improve life or improve the process by intermediate stages of annealing and let the grain grow back. While that is a specialty by itself, as part of the material thing, it has a bearing on this. Of course, I can't say you can't, you don't need it here, but we can concentrate on what we need to do here. So far the bending allowances which we have talked about are about taking the internal dimensions and adding something to it as a bend allowance. This is what we have been doing all along. Another way of doing it is saying in some cases we probably have only the external dimensions which are measurable. Alternatively, only the external dimensions are of interest to us. So please have a look at the sample which I would like to show you here. This is what I was talking to you about, this being a hat section. This particular thing actually is from a box which holds a switch gear. Switch gear meaning all those various types of things which use the DIN C clamp mounting. So if you see here, we are not that much really interested in the internal dimensions as we are interested in the total height, and then we are interested in the various features, what is the depth here and so on. So in such cases we invariably end up with having to find out the total dimensions outside and eventually subtract the extra material that may come about. I will get back again, I will give you a special lecture on this. In this case you can see this is a small aluminum sample which I have used earlier to make sure that what I am talking has a practical and same thing. And now this lecture today is going to talk to you about, imagine there are two sections in which part of it is like this and then we have a corner. How does one cover the corners? So as I go along, I will also show you a small method. Actually if you remember, I started this in the first lecture saying you learn how to make a cardboard simulation. This is not actually a real product, but then I just wanted to show you that in a very short time it is very much possible for us to simulate items like this without too much of bother of having to fabricate a piece and then what do you call, end up with not being able to modify it. It is not as serious as this. This one is my hearing aid box. In the case of this hearing aid box, tremendous amount of detail has been worked inside such that it can be opened well. But even then if you start with these things like where do you split the box, followed no, where you split the box, and then how do the top and bottom join together, and then if we have a clasp here, how does it work, and so on. As I pointed to you earlier, a lot of it depends on how well, what is the amount of money you are ready to spend in making the detailing perfect. If it's a simple throwaway item, obviously you don't add too much to it. But if it's a cosmetic item, or in my case, if it's a very, very highly functional item, which I need to carry all these things, a tremendous amount of interest and detailing time is spent so that things look okay. So if you have to come to cosmetics, including powder compacts, rouge, and then all your various types of sprays and what you will find in a shower, lot of those shower gels and all that, a lot of effort goes into making the detailing on the top. Now getting back to my exercise, I mean the actual lecture here, you will notice that same thing, the K factor seems to be uniform, is a ratio that represents location of the neutral sheet with respect to the thickness of the sheet metal part. So using radian calculations and so on, they have come out with lot of these things which I tried to tell you about yesterday. Then there is this issue of a setback and bending allowance and so on. Extremely well and straightforward, provided we know the correct K factor to use. Once again, most accurate way of finding the K factor is by using reverse engineering method described, and calculating the K factor use as described later. They talk about the reverse engineering, it means make a sample, bend it and get back, because it is a physical phenomena. The equation does not follow the, the equation does not cause the phenomena, it only describes the phenomena and then how we can use it. As we go down, you see here one more time, I may have repeated, even here no, it comes from probably either it is called, I think, Bend Works. I do not know which program uses it, but you see the caution everywhere. It is important to bend the sample piece in the same manner as you plan to bend your real pieces, so that whenever you measure now becomes reproducible later. Seen that, no, total flat length versus what you get here. The bend radius can be extremely difficult to measure accurately. In the case of a not critical application, we are interested in a number to use in our CAD program that with the bend radius used in our program will produce the results you are measuring in real life. So if you go down further, a lot of these things are explained below. So as I have told you about it, no, saying what exactly is air bending. In air bending, there is no need to change any equipment or dies to obtain different bending angles. What is done is, you see this top and bottom, you have two dies and then you see the radius here, and then as it moves inside and comes back, you end up with soft material, medium and hard material. What is the K factor? So as you make the punch move down a little, you can get more or less of the included angle. And then something else also is, because of this air bending, natural flow of the material, and especially if you use an hydraulic thing and slowly, it seems to give you consistent better results. The other option is to call bottoming. Bottoming is a bending process where the punch and workpiece bottom on the die. This makes for a controlled angle with very little spring back. The tonnage of this type of press is more than air bending. The inner radius of the workspace should be a minimum of 1 material thickness. Earlier I told you that it can be 0.1, 0.2 and then 3 times and so on. In this case, no, they have given. So you see here, if you carefully see here, this punch is, holding it hard and making it bend. seen this, no? You have a die and a punch, and then it is pushing all the materials inside. You see here there is still a small bit of a gap here. Now going down, you really have a bending process in which the punch and the workpiece bottom on the die and compressive stress is applied to the bending region to increase the amount of plastic deformation. So, you see here a small detail. This detail actually we need not, a typical what you call equipment constructor need not break his head too much about it, except to know that a fabricator goes through all these things. And then when you make a design, better to consult with them first. So, you see here, if you see the exact corner here, you see here there is a small relief also given here, then there is another some device here which pushes the thing here. So, you see that various types of these operations are given here. Bend radius should, if possible, to be kept at the same for all radiuses in the part to minimize setup. Ideal minimum radius should be at least 1. Bending perpendicular to the rolling direction is easier than bending parallel to the rolling direction. In rolling, we mean the material which comes out of the what you call rolling presses. In the case of a rolling press, you have a continuous strip. So, if the strip is available in this direction, it means you can bend it here like this. It comes continuously, and then bending it here is like that. If you try to bend it in the other direction, chances are it will crack. Now, you see here, hot rolled shield can be bent parallel to the rolling, but in the for cold rolled sheet we have a little problem about this thing. Minimum flange width should be at least 4 times the stock thickness plus the bending. Violating the rule should cause distortions in the part or tooling or operator due to slippage. Once again, relatively important point. So, we have here, you have seen this. If you try to hold this and do, chances are it will pull inside. You understood, no? If you take the corner and trying to do something, chances are this edge will get pulled inside, especially if the object is wrong. So, to overcome that, they have means. Generally what they do is make something longer and then shear off the unwanted portion. You can even have it 1 thickness. So, they will put another 1 thickness sheet here, and remaining they will shear off. So, you have it, but the original operation is now repeated by 3 more operations. After the original operation, you have to take it out, measure probably or check with the gauge, and then pass it through another notching stage. After notching again, no, maybe you have to do dressing and all that. You end up with multiple handling of the equipment if you violate this here. So, flange width, it is just a matter of convenience. They have given here saying thickness and bend radius and so on. Slots or holes too close to the bend can cause distortion. Holes should be located minimum. These are all matters of simple design guide rules. Dimensioning the part should take into account the stack up of dimensions that can happen, and mounting holes that can be made oblong should be made, and then parts should be inspected and in the constrained portion and so on. The issue being, I think while he was marking it there, while the marking was going on there, you were told that cumulative dimensions are used like this. You have seen this, no? So, something has been made, and then after that, starting from a datum line, things are added, and then wherever we have this bending, a bending allowance has been added, and all the marking has been done with respect to a datum line. There are certain advantages to this, except when it is symmetrical and depending on accumulation of errors. If you see my colleague there, he did it in a slightly convenient way. He had marked something from this side, turned it over, okay, and again marked something from the other side, so that the symmetry is maintained. In our case, no, if something becomes little more or less, does not really makes such a lot of a difference. And then you can see a small bit of detail here in the corner, which I will come back to later. You see here there is a small step and all that. I will come back to you later about it. Now coming back to my this notes. In V bending, the clearance between punch and die is constant, equal to the thickness of the sheet blank. It is used widely. Sheet ranges from 0.5 mm to 25 mm. Tough, really tough. And then you see here things like that hat section which I showed you. U-die bending is performed when two parallel bending axes are produced in the same operation. A backing pad is used to force the sheet contacting with the punch. It requires 30% the bending force for the pad to press, and so on and so on and so on. Why this is done is, if you are to have a cumulative bending, and then it may not be possible for us to put something else here and then clamp it here. Once the U is formed, clamping the U again, it is a little problem. There is no way of continuing the other bending. So bends are close together. Typically this operation is done, and sometimes even in the case of the hat section, even the other operation can be done here. If you put the other material, easily you will be able to make such things here. Then you see here slowly we are getting into a few specialty type of bending, saying why do we need to just follow those things. The blank holder and pad are there, flange length can be changed, and the bend angle can be controlled by the stroke position of the punch. There is a little specialty items, but then maybe it is just worth knowing. If you go down, we have stuff where you have seen this, no? Various types of other operations. Double die bending can be seen as two wiping operations acting on the workpiece one after the another. So we have something here which first makes a contact and does, afterwards one more and it does something. Then we have all these beautiful rotary bendings. Looks good. And then a big list of references here. I suggest you look up these things. Now I will show you few other things from my nice collection of samples here. Okay. Yesterday I wanted to show a sample for you of this item. See here, if you remember, I was holding that small box. So try to make a, what do you call, a design like this, and in this design, oh, which way am I bending? Oh, I think I should bend this side. We have several nominal dimensions which covers the top here, then the bottom here, and so on here, and then somehow I need to make sure that the top and bottom fits here. From the CAD convenience, we have ignored the material thickness, but we can't get away with it in reality. But when we make a cardboard box, I will just show you the thing. This was given to our same professional who does all these things. You see here, after developing the sheet, this is the development drawing. This is the development drawing as he has done. He has happily removed all the materials we want very carefully on two counts. Why it is being shown is that you will understand what it is. Secondly, it is a little like the magic sculptor. Somebody asked a sculptor, it seems, saying, how do you make all those beautiful art pieces? He says, oh, nothing, I look at the rock and remove all the unwanted pieces, and then it remains. What remains is the wanted piece. It's tough for us to do, but then if you look at my, what do you call, monitor, you will be able to see things that have been done. So after the sheet has been cut out from there, very carefully, a lot of interest, has been taken to ensure that cuts are taken perfectly, and then this one is the bottom portion, this is the top portion. No allowances of any sort has been given. You just make sure that things fit. See that what the picture earlier shows you in one direction, slightly better here, and now you see miraculously these things seem to join with each other without any problem. You have seen here. I will try to focus in the corner. You have noticed actually there is a little pile up. Though we started with no thickness, we seem to end up with a small, something which is trying to push into the other corner, which happens here also. Though the thickness is very small, in this case the sheet thickness is probably around 0.6 or 0.7 mm cardboard, still we still see the problem. Little closer view. It is actually a small object, and then to make it hold shape, another of my colleagues is trying to hold them together, and then he has applied this Fevicol. Fevicol is nothing, it is a trade name for any of these modern cardboard glue which you would have used in school. And then after that, see the top and bottom have been attached together. See here, so far the bottom is made, and then the top was only a preform. Seen that, no? That is just a preform. After sticking all these parts together at the bottom, he has just attached it to the top, and then you see we have a beautiful, nice compact box. This is what I was talking to in my first lecture. You remember, my first lecture, I told you should learn to make all these small items. Two things are here in this. One of them is, in the earlier extension we just took a standard existing some unit we had, and then I said a multimeter is probably something which is good, okay. And then this one is imaginary, but more for the purposes of showing you how sheet metal is affected by these things. So you can see I have as I go along, I wanted to show you a very, very interesting thing. See, if I have to make a sheet metal cup, it is possible for me. You understood? The internal radiuses have been taken care of, external radius also has been taken care of, but the only thing point, in reality, it is unlikely that you will have sharp corners. If you want to make a cup like this, which is quite a lot like the cup I have here, seen here, this is another of my boxes. It has radii all the directions. That one is a little similar to this cup. There is an internal radius, and then thickness has been added. To the internal radius, thickness has been added, and the corners also, externally they have these corners. It looks nice. And then one small bit of detail which is not visible is that small thickness, half the thickness has been removed here, and in this top there is a small catch here, and the whole thing snaps, and I have a smooth enclosure which goes neatly into my pocket. I carry my hearing aids. So coming back to my monitor, what is shown here, this sort of thing can be done only using a technique called deep drawing. In the case of deep drawing, we have a cavity, outside cavity which forms this, and then we have this inside cavity. That inside cavity and outside cavity form an object like this, but in real life we will notice that this cannot be done by a simple sheet metal operation. When we do sheet metal, we end up with this small issue about how to join the corners. You see here, we have a thickness here, we have a thickness there, and something happens and the whole thing, because two thicknesses are involved, something overlaps there. It is not as easy as we think it is. Corner is still tough. You want to completely avoid the corner, we end up with giving a radius fully here. You have seen that there is a radius, and complete the radius has been relieved, but these are not suitable for external operation. So, how do we overcome this small problem of this corners and this? No, we need to work a lot more about it to see where we come with these things. I do not know if you remember, this is quite a little like the box I was trying to show you yesterday. Very conveniently, I glossed over this corner, okay, just glossed over it because too early. If we confuse ourselves with all these details, now you will suddenly notice, while in a CAD drawing it is easy to make these 3D rendered objects, in reality what you will end up is most likely this corner is most likely to look like this. Seen that, no? It is not a matter of just ugly, it is not fully functional, not at all functional. So, you need to spend a lot of time worrying about this detail. So, right now I will go back to a few of my samples, if our people can show me these things. While this enclosure all has rounded things, this one no, seems to be a little more flatter things. This can, with a little bit of what you say interest, is very much possible to for us to fabricate a small unit like this. This is the unit which is what was being shown. So, while things look okay when we try to show them in the workshop, in reality the corners and all do not match well, and there is a gap here actually. It's oscillating, in fact it is not even touching it properly. Two of the limbs have been, they have been able to manage it, but in this limb, because of the closure in the end and so on, it is not possible to close these things. So, if you really want a perfect square in the corner, if you want to make a perfect edge, our choice is probably to continue with welding. This is one of those which I have shown you earlier, a shielded arc welding, in which either argon or some other gas has been used, and then fillet it have been put inside, and then outside it looks flush. Similarly, on the other thing, if you were to weld it on the outside, inside will probably be flush. So, you can play around a little with these things. It looks a little like that gusset which I have shown you in the other day's lecture, and it is not as if rounded edges are only the answer to all our problems. So, in real life, you see here I showed you two things, both of them use that same 18650 cell inside, round, some benefits, it makes it looks a little like some other object. In this case, see that extra volume, actually volume appears to be about the same. Same cell is in this, and then we have something which gives us slightly more work. This can be also done by sheet metal. This can probably done by taking a tube like the high HPVC or mu PVC tubes, and then building up all our things inside. Same things can be done probably if you have an aluminum extrusion, you can make it. In this case, it is made out of some thermoplastic, so that injection molding can be done. But if there were to be heat generating components, we will probably be using an aluminum extrusion, or we can even assemble it using these ordinary whatever workshop items you have. Just like I have shown you the section where we have two things being close together with a small step. You will see this in most of these things. You see here we have a top and then we have a bottom, and then if you remember I was talking to something about if you cannot hide something, highlight it. Next time look around all the injection molded parts you have. They do not really close because the human eye can easily locate relative differences. So, intentionally they leave a gap, they make a step and all that. Overall that part looks quite precise, absolutely no problem with it. Having shown a few of these samples, now permit me to go back to this whole thing. So, in reality this is not easy to produce. You have seen this, no? Well, it looks nice, it is not that easy to produce or anything. Same box which I showed you here, this is did not have a thickness. This is what has been done in the cardboard thing. But then as you come here slowly, we have added the thicknesses here. The moment you add the thickness, we end up with two issues which I thought, no, I will highlight one more time here. One is you have seen here there is a bending radius inside, it is real. Similarly, there is a bending radius here, real. And then the moment you have an internal bending radius, chances are there will be an outside radius also which will be part of it. Seen this here. If I go a little closer, while the inside bending radius is clear here, outside also sheet thickness, internal bending plus sheet thickness will come. And do you need the internal bending radius? Yes. Otherwise, the sheet is likely to tear apart. This is the reality of sheet metal. Well, again, very conveniently, and to avoid confusion, I have ignored several things. One of the features you will notice is, while there is an internal bending radius, this bending radius is supposed to sit here in this corner, seen here. So, there will be a clash. This will not fit here unless this is smoothened out on the outside. So, in the corner here a little bit of smoothing is required, and same thing happens here also. If you are to come to the bottom here, it is not honky dory. See that I have shown a sharp corner here, and then conveniently it has been stopped here. That is not likely to easily fit into this corner. You need a little rounding off here, or you need some other operations there. So, what looks otherwise as a simple this thing, no, it really does not close so well. It will be a lot like the other sample which I have shown. You have seen this. This is more like what is likely to happen. So, you need to take a decision about which part overlaps what. In this case, there is a bend here. Internal plus external radius is taken. There is another bend here. Internal plus external has been taken care here. If you want to avoid, you need to probably leave both the thicknesses visible here, and with another internal radius also, which is the sample which I have shown. But in reality what they do is they make this overlap a little and then make some special care is taken to make this follow into the other thing. When it bends, it normally it becomes a square. It will just be a square. After that, after the bending is over, they have either gently pinned it, or they have filed it to fit the other operation. This is sheet metal reality. But then why do you need to learn? You see here it started here, you see here it is sharp, and then but in the corner we have a radius here, we have a radius here, and then there is a unspecified thing. If you are to make it flow here, you need to do the other adjustments which have been done. So, probably this lecture has been hopefully enough informative. Seen here, it is not, you do not want any clash, you end up with a completely open thing. So, this is one of the I will see whether I can continue or I will stop here. Now, going back here, you see here everywhere, whenever there is a corner and whenever this type of operations are done, sometimes these are all done to accommodate other limbs also. Imagine if one of these ends were to be closed. So, in the blank there would have been a limb which is a little longer, okay. And then just as you have a punch and a two-sided operation is there, we can have it on all the four sides. So, you have a cup like thing, the punch forces inside, and then when it comes out you have a beautifully formed part. So, we have two angles, flat, imagine the whole thing is flat, okay. So, you have all the four type of these operations are there, you make a punch, push it inside, and all four of them close very well. Only in nature and in organic they grow into that, but in this case we still end up with probably small corners like this, or you have to do something to take care of all these edges which are there. I suggest you go over the whole this thing one more time, and then it is not as if plastic things are easy. If you make something out of injection molding, this one is taken from some mobile charger which was probably put to a bad use, okay, and then it burnt out. But you see here, even here now, they have all these nice corners everywhere, and in this corner we need to give slots so that air passes. It did not help, just drilling holes all over the place did not help. Just have a look and see, and then after that I need not bring you back to this for some time. It is not as if last thing about bending allowances has been done. Just as it is treated as a empirical operation without understanding what is going on inside, here there are people who keep working on these what do you call these sheet metal flow operations. Especially you have something called metal forming definition, and then later on some people have been working on it to find out what is the bending allowance to be given and so on. Well, so far what I have shown you has been what you call more about a industrial practice. The things like K factor and all have already, people have been working on it, and released notes are available in the public. So, if you see here, this is not very different from what you have shown earlier. While that is, they claim a intellectual property on this. This is in keeping with the tradition of our open access to various documents and all that. A lot of this stuff is also available of the academic net. So, experiments have been carried out, and then gauges, millimeter gauge, and then type of material, and then the things have been reported which are verifiable. Whole thing are reported, and then there are several publications other than trade journals where it is possible for us to take care of all these things. Now, the issue being, you see here, CAD/CAM programs can estimate the dimension of the sheet metal piece required to bend, produce 3D object that the engineer is drawing. Life has been made simpler with analytics already having gone into the various types of operations. So, we have here how the K factor gets accommodated and so on. So, and then most important, have you seen here saying coefficient of friction with stress has been observed for steels for slow velocities as the ones occurring and so on. So, the amount of different types of forces and then the reproducibility all of it is available in books. Still, small compensation, no, saying for a smaller die width what happens, for a longer die width what happens, lot of this information is available. Since some of you are the electrical engineers, you are all familiar with application notes. So, if you look at anything, a small thermistor, or if you look at an LDO or anything, there is usually the title sheet contains a little bit of the extracts. Bottom sheet gives you the full actual behavior and what is it that is committed. So, you see here lot of stuff about punch shape and all this stuff now is available of publications. So, you can always go about and then try to do understand these things, so that to see in case there is any mistake, is it mistake of, so far we are assuming that all the machines are maintained well, there is no gap or shake or anything of those things between the punch and die, alignment, and whether the forces are centralized or not. If you are sure about these conditions, you can now work on all these things and then end up with a very convenient, reproducible width of blanks. Once you have blanks reproducible width, things will work very, very well. And then two things are there. One is continuously you need to update all the tooling. Secondly, the material condition should be checked. So, thank you for today, and then we will meet again with that next level of things. So far I have talked to you about the highest abstraction level, saying how do you try to think of products and so on. Then second level I have tried to take you to our fabrication facility here, saying using sheet metal we can fabricate certain items, and then for purposes of sheet metal I have told you it is very easy for us to make all these nice models. Okay, it is cardboard, it is not necessary child's play. And then if you want to accommodate thickness, you can always make things out of a thicker board. And then finally, if the same thing can be reproduced in plastic materials, typically if you are only concentrating on the shape, commercial polystyrene sheets are available. And then you also have foam boards, then you have polycarbonate, then you have acrylic, then you have I do not know what are the new types of materials, and there are say various types of foams that are available. If you are to make a mouse, you can use an acrylic foam to model this. You take it and then you try to scrape the foam, and the magic is now with the advent of rapid prototyping, you can scan the object and reproduce it directly in a 3D printer. So, in 3D printer also next lectures I will see whether I can arrange for a demonstration. The easiest I suggest for you is that learn how to make things out of sheet metal and then also plastics. So, most of these things, the main advantage of plastic is it is insulator. You need not worry too much about what do you call, how to make sure that you do not short circuit something. In the same way, the disadvantage is they are not EMI and EMC proof. So, you need to worry about it. Sheet metal has the positive advantage of its being very strong, and then if you make it in magnetic materials, the shielding is better, and if you make it in non-magnetic materials, electrical conductivity is still ensured. Normal conductive EMI and those things behave much better, and then ultimately strong beyond belief as compared to plastic. And then sheet metal, if you make it if you make the drawings and use all the various techniques, there are enough people out there who will convert it to CAD drawings. So, I will see if I can take you through a little bit of a CAD exercise. Similarly, if I can take you through a little bit of a plastic exercise, saying how do I join plastics and so on, in the end show you one or two materials, or I am sorry, projects which completely are fabricated for each type of thing. So, thank you for today. We will probably meet again. Thank you.